Okay, in this lesson 10 we are going to discuss induction motors. Previously we have discussed the first type of three-phase motors, which was the synchronous motor. Now in this lesson we discuss the other type, which is the induction motors. One, the contents will be basic construction, then the basic concept of how this motor works, then the concept of rotor sleep, which is very important to understand when we discuss induction motors, and finally the electrical frequency of the rotor voltage. Okay, in terms of the motor construction, still we've got two main parts in the motor, which is the stator and then the rotor. Yeah, the stator, when we talk about the stator, is basically the same, yeah, design as the one that we have for the synchronous machine that we already discussed before. Yeah. However, the rotor construction then it will be different, and there are two different types of induction motor rotors. The first one is the squirrel cage rotor, and the second one is the wound rotor. On the right hand side of the slide you can see both designs. The bottom one is the squirrel cage, and you can see why it's called the squirrel cage, because of the shape has resemblance to the squirrel cage. And this basically consists of parallel bars. Yeah, it's got parallel bars. Okay, and you've got shorting rings at both ends, shorting the ends of the rotor bars electrically. Okay, and the other type of the design is called the wound rotor, and you can see it on the top here. Yeah, this is one rotor. It's got three-phase windings, and you can see it has slip rings, yeah, which allow us to connect the three-phase windings to variable resistors, and by doing so we can then, for example, control the speed of the motor. Okay, and on this slide we can see the comparison between the two rotor designs. The first one is the one rotor, and the second one the squirrel cage rotor. So in terms of the construction, the one rotor is more complicated and more expensive, while the squirrel cage rotor is generally simple and cheap to make or to manufacture. Okay, and for the rotor, as we have seen before, that the one rotor consists of three-phase windings, while the squirrel cage rotor consists of bars which are shorted at the ends by using these shorting rings. With the one rotor being able to connect the three-phase windings to variable resistors allow us to do speed control by rotor resistance, and this won't be possible if we use the squirrel cage rotor, as the resistance is basically fixed. And in terms of applications or the usages, one rotors are generally used in applications where high torques are required, while for the squirrel cage rotor is the other way around. Yeah. Well, in the applications where the high torques are not specifically required. Okay. Okay, and then how this motor works. First we apply the three-phase voltage to the stator, which will result in the three-phase currents flowing in the stator, yeah, stator windings, and this then in turn will produce magnetic field which is rotating, and the explanation has been given in the previous lessons. yeah, how these three-phase currents generate this rotating magnetic field. And this magnetic field is rotating by at the speed given by the equation here, and sync equals to 120 times Fe over P. Fe is the frequency of the three-phase voltage that we apply to the stator, and P is the number of poles in the machine, yeah, in the stator. Okay, and this rotating magnetic field Bs, the stator magnetic field, passes over the rotor bars, and then it will induce a voltage across the rotor bars, and the voltage is given by the following equation. E induced voltage is equal to open bracket V cross B closing bracket dot L, yeah? So it's a function of the V is the speed, yeah? The speed of the bar relative to the magnetic field, and B is the magnetic field density, and L is the length of the bar. Okay. Okay, the voltage induced across the rotor bars then will produce currents flowing in the rotor windings, and this current then will induce magnetic field Br, yeah, rotor magnetic field. And the presence of two magnetic fields, which are Br and Bs, while Bs is rotating, will then in turn generate or induce torque in the machine, and the torque is given by kBr cross Bs. Okay, and again, if you remember that this happens because the attempt for alignment between the two magnetic fields, and Bs being rotating, Br try to chase Bs, yeah? And then therefore the rotor is rotating following the rotation of Bs. Okay, and yes, the rotor will accelerate in the same direction as the induced torque. So it will gain speed, yeah, the speed will be increasing until it's get very close to the synchronous speed. The speed itself will not reach the synchronous speed, because assuming that it's reaching that speed, the relative speed between the rotor and the magnetic fields will become zero. It would become zero, and if it means that then there won't be any voltage induced across the rotor bar, because it's a function of the speed, yeah? You can check again on the previous slide that the induced voltage is a function of the speed among others, yeah? So if the relative speed is zero, then the induced voltage is zero, and therefore there is no rotor current, and therefore there is no Br, and hence no torque will be induced. So if there is no torque is induced, then the motor will be subject to deceleration. It will loses its speed, yeah? And this is why it never it doesn't actually reach and stay at the synchronous speed. So the steady state speed of the motor will be close to the synchronous speed, but it's lower. Okay, and this slide summarizes the operation of this motor. First of all, we've got the three-phase currents in the stator, and this will produce rotating magnetic field Bs, and the Bs or the stator magnetic field will then induce voltage, yeah, across the rotor bars, and then the current will flow in the rotor windings, and then this current in the rotor winding will produce magnetic field, another magnetic field called BR, and the presence of BR and BS will produce the induced torque following the expression KBR cross BS, yeah. And then therefore the torque will cause acceleration of the machine, and the machine will gain speed until its speed gets very close to the synchronous speed, yeah. Especially when there is no load connected to the motor. Okay, now we'd like to discuss the concept of rotor slip. The concept of rotor slip is very important one when we discuss induction motors, because by understanding the concept of slip or rotor slip, then we can use this in the analysis of the motor, for example in terms of power, yeah, in terms of the speed itself, yeah, and some other stuff. Okay, what is slip speed? First term, new term here is slip speed, is defined as the difference between the synchronous speed and the rotor speed, yeah? So n slip is equal to n sync minus nm, yeah? N slip is the slip speed of the machine, n sync is the synchronous speed, and nm is the speed of the motor or the rotor, yeah? Then we've got another term called slip, yeah? And the notation for it is S, which is a ratio, yeah? It's the ratio of n slip to n sync, yeah? So it's n slip over n sync. Okay, and n slip itself can be replaced by n sync minus nm, yeah? As you can see, as described in the previous equation. So the slip S is also equal to n sync minus nm over n sync. Now we've got a couple of questions here. If the rotor turned at synchronous speed, what is the value of S? Yeah. If the rotor is turning at the synchronous speed, it means that nm is equal to n sync, and therefore the slip S will be n sync minus n sync over n sync, which is 0, yeah? So if the rotor is turning at the synchronous speed, the value of S will be 0. And if the rotor is stationary, then again the question is, what is the value of S? If the rotor is stationary, then it means that nm is equal to 0, so therefore S is equal to n sync over n sync, which is 1, yeah? So this is these two answers of these two questions give us the range that we can have for the value of S, which is from 0 to 1, okay? And again, 0 is when the rotor is 0 is when the speed is equal to n sync, while S is equal to 1 when the rotor or the motor is stationary. Okay, and yeah, then if you rearrange the equation, then you can get the two equations for the speed of the motor or the rotor shaft, yeah? There are two different slightly different equations here, depending on the units of this rotational speed that we use. Okay, the slide here, we're going to see the electrical frequency of the rotor induced voltage, okay? Which is, interestingly, the frequency is not constant, yeah? it's actually a function of the slip, as we will see later. Okay, the induction motor works by inducing voltages and currents in the rotor of the machine, and for this reason it has been called a rotating transformer. So the basic principle is very similar to a transformer, where in a transformer we've got the primary and secondary winding. So if you apply a voltage, an AC voltage to the primary winding, then a voltage will be induced in the secondary winding. So similarly here, we apply AC voltages onto the stator winding, then voltage will be induced in the rotor windings. Yeah. However, the difference here, then we've got a rotating part. The rotor is rotating, and therefore this induction motor is also called as a rotating transformer. Okay. Okay, another difference is that unlike a transformer, the secondary frequency is not necessarily the same as the frequency of the primary frequency, the primary voltage. Okay. Okay, if the rotor is locked, let's say we lock the rotor, so it cannot move, then it will have the same electrical frequency as the stator electrical frequency. Okay? So FRE, which is the frequency of the rotor voltage, will be equal to FSE, which is the frequency of the stator voltage. Okay, that's if the rotor is locked. So it's in this case it will be exactly the same as a transformer, yeah, which is the secondary is not moving at all, and the frequencies of both primary and secondary will be the same. Okay, now if the rotor is turning or rotating at the synchronous speed and sync, then the rotor's electrical frequency FRE will be 0. Okay, so this is the two extremes. Okay? You've got the same frequency or 0, and for any speed in between, then the frequency of the rotor will be equal to S times FE, where S, if you remember, is the slip. Yeah? It's the slip of the rotor. Okay. Okay, so from here you can see that the frequency will be a function of the slip, and in another word, it will be a function of the speed of the rotor. Okay, the other two equations that you've got in here is just rewriting the first equation by using the definition of the slip S. Okay, this is the example of a question of analysis. We've got a 208 volt, 10 horsepower, 4 pole, 60 hertz, Y connected induction motor, and it has a full load slip of 5%. Okay? And the questions are, first, what is the synchronous speed? Then what is the rotor speed of this motor at the rated load? Then what is the rotor frequency at the rated load? And finally, what is the shaft torque of this motor at the rated load? So let's just quickly go through the answers. Okay, here are the how to answer those questions. I think there is nothing really tricky. They're all quite straightforward, yeah, and we just use the equations that we have seen before. Yeah. So the first part A, the synchronous speed, we just use the equation that it's equal to 120 FE over P, And then when part B, for the rotor speed, we use again one of the equations that we have discussed before, that the Nm is equal to open bracket 1 minus s closing bracket times n sync. Yeah? There is a slight mistake in the textbook, yeah? Especially this is the one of the older versions. So it's supposed to be 1 minus 0.05 times 1800 rpm. Okay, and then for the rotor frequency, we can use the equation that it's equal to SFE. Yeah? S again is the slip, which is 0.05 times FE is 60 hertz, so give us a value of 3 hertz. Okay, and then to find the torque, we use the equation for power. Yeah? The output power is equals to total load times omega m, and then if we erase this equation, that the torque, the load torque is equals to the output power over omega m, and the output power is 10 horsepower, which is given as the rated power of the motor, but we need to convert it to watts, so we multiply it by 746. Yeah? And then for the speed, is given in RPM or revolution per minute, so we need to convert it to radian per second, and the work can be seen here. Yeah? And we should get a value of 41.7 Newton meters as the answer.